Hi, this is Robert Bolaños. Welcome to the analysis and design of a flyback video 33. Okay, I'm going to talk a little bit about a very important subject, and that's thermal impedance. Okay, I'm going to try and make it a little quick, and then later on I'll expand more into it. But the thermal analysis is used to calculate basically the temperature junction of a electronic device. It could be a diode, it could be a MOSFET, it could be a transistor, bipolar transistor. Okay, and typically when you're talking about temperature, these are mechanical uh, ideas, so to speak. Let me go ahead and erase this part. They're they're in the I guess you can say that it's in the mechanic or mechanical engineering domain. But fortunately, this thermomechanical, we can actually have an equivalent. We have an equivalent of these thermal mechanical. We have a electrical analog to it. So when we're talking about in mechanical as power, it can be power as horsepower or watts in that case. But when we do the translation to an electrical circuit, the power is represented as current. Okay, and the units of current, it's amperes or amps. And then in the mechanical, the thermal impedance, the units are in ohms. But in the electrical, it's resistance, and its units are also in ohms. Okay, and then temperature, which is also mechanical unit, that's in Celsius, but it has an equivalent in the electrical world as voltage, which the unit would be volts. Okay, so here is the data sheet of the IFR 150, and that is the unit or the device that I used in this simulation that I showed in the last video. If you haven't watched the last video, please watch the last video. On the last video, when I change the normal ratio is 0.5, but when I changed it to 0.1, I made a statement that if you do not set the turns ratio correctly, that you can end up with a much higher voltage in the drain. And I demonstrated it by changing it from 0.5 to 0.1, and I ran a simulation, and it showed that the output, which was supposed to go to 12 volts, did not go to 12 volts. Instead, went to 6 volts. And then we saw that the drain was clamped at 100 volts because this is a 100 volt part. And I had mentioned that this part, if it continued working, that it would heat up and burn up, but I didn't show that yesterday. So I thought about it and wanted to see if there was a way that I can show it through simulation, and I come up with this little circuit. This circuit, what it does, it's a current source. Okay, remember I had mentioned that power, what we want to do is we want to be sure that we deal with, basically what we want to do is we want to deal with currents, resistance, and voltage. So remember, the current will be power, resistance is still resistance, and a voltage is temperature. in Celsius. Okay, so keep that in mind. So this I will represent the power. Okay, it's a current, but remember that it's representing in the mechanical world the power. But which power? Well, it's calculating the power of the IRF 1 to 50. How does it do that? If you notice here, it says V times I. So what it does is, right here, we break the leg of the source and we route it into the current measurement. This node measures the current going through the transistor. Okay, so it measures it, and that value is placed there. And then this node is measuring the voltage across the drain to source. So it measures the drain to source and the current through the MOSFET, and then multiplies it together. And when you multiply the voltage and the current, you get power. In this case, power is going to be represented as a current source. Okay, so that's basically the model that I wanted to show you. That, hang on, one. That if you're going to do a real simple thermal analysis, you typically calculate what is the power level, the power of the MOSFET. You can calculate that by hand or simulator. So if you get, let's say, 2.3 watts, then you do a current source of 2.3 amps. So in this case, we could put 2.3 amps, and then we ground that. And then the first connection is the junction, the temperature of the junction. Okay, and then it goes into the resistor, and that first resistor will be a theta, R theta, JC. Okay, where do you get this theta JC? Well, in this case, here is the data sheet, and we look here where it says thermal resistance. It says theta JC junction to case, and that would be 0.83. Okay, so this unit, we go ahead and, oh, I'm sorry, I had mentioned that this is in ohms. It's in ohms per watt, and what you do is you change it into ohms. Okay, so in this case, when we do the electrical, we're going to put a 0.83 ohm resistor. Okay, so this theta or JC says that this J is going to be on the left side, that's the junction, and this C, this is going to be the case. Okay, so that node is there. So then you typically, when you mount on a board, let's say your board there, and you have your transistor mounted here, well, that's a case. I'm going to put C for case, but the board temperature may be at 25 degrees. Okay, so you also have a thermal pass where the heat is flowing, and there's a resistance from the case to the board. Okay, and a typical number that I use at work is R theta case to board of about 10. So I'm just going to go ahead and put that here. Okay, R theta case to board, and I'm going to assume that the board is at 25 degrees. Okay, so remember this case is right there, and that base will be here, or board. Okay, so the board typically can be higher, but we're going to assume that the board is at room temperature of 25 C. So to do that, we simply put a voltage source, and this is ground, negative, plus, and since the board is assumed to be at 25 degrees C, the analogy is to make this into 25 V. In other words, your voltage source is going to be 25 volts. That means that this node, when you do the measurement, will be 25 volts, which represents 25 Celsius. And then this current, as it flows in this direction, if you notice, then this is positive, negative, positive, negative. In that case, the temperature goes up. So then that node will be at a slightly higher temperature, and whatever the voltage, it may be, let's say 80 C's, which is really 80 volts. Okay, and then the temperature that you read at this junction, that is the junction temperature. Okay, and you don't want for it to go higher than either, here is the derating. So basically, you don't want the junction to go higher than 125 C or 40 C below the manufacturer max rating, temperature rating. So if this temperature exceeds any of these, you're going to fail. You're not meeting the rating. Okay, so now that I already explained that, then this should make sense. Here, let me go ahead and reorient this. That way it'll be consistent. Okay, here is, I'm labeling this node as TB. The temperature of the board is that node. I already said that the board will be 25 degrees, so this is 25 volts. Then this node will be the case temperature. Okay, and this is the resistance of J to C. And let's go ahead and change it to the proper one. I think it was 0.83. 0.83. 0.83. Okay. And then what I did is, now let me explain. I put a little bit of a capacitor here, and let me explain this, because this is a switch in power supply, so the current or the power actually looks like this. It's high peaks. Okay, so these peaks, it's hard to get an average, but if you put a capacitor, then the capacitor will start charging and it'll average out the pulses. So the average voltage is actually the junction temperature. Okay, so let's go ahead and see if we can let's go ahead and put this at 0.5, and this configuration, it should work properly, and the IRF 150 should not get hot. So let's go ahead and run it. Okay, so in this configuration, the output should be 12 volts, and the temperature should not get anywhere near the 125 degrees. Okay, so here is the output voltage. It goes up 12, and then here we look at the temperature. So here is the voltage. So VTB is 25 volts. It's 25 volts right here. But then we take a look at the junction temperature. So the junction temperature, the highest, is the blue one. Okay, and it's about 30 degrees. Well, the case is only 30.7, 30.2, so there's very little rise. So this is very cool. It's not getting hot at all. Okay, so now let's go ahead and change this to 0.1. And remember, yesterday I said that because we changed the windings, this drain will be saying higher than 100 volts. So the internal diode that's inside will avalanche and act as a zener, and it will clamp it, and it will be conducting power. So let's go ahead and run it again. Okay, so in this configuration, it should get very, very hot. Remember, we only got up to less than 31 volts, which is 31 Celsius. Okay, now look at that. Look at this, folks. Let me go ahead and take exactly what I had said yesterday, that it was getting hot. This thing is really burning, and if you were to let it run, it would probably see smoke. See right there, that's about 120, 25, so it's already exceeding the junction temperature. It's around 300 degrees. Okay, so that's extremely hot. Okay, so of course something will pop. You'll probably pull your circuit current limit on your power supply, or something will burn up. So anyway, this is your proof that yes, that this is one of the ways that you can calculate your thermal uh, junction, whether your transistor is getting hot or not. It's a very nice trick, a little simple model that you can use to simulate and check your designs. So if you have any questions, I welcome any comments or tips if I'm explaining this correctly or not. I'm always willing to improve on my presentation. So if it made sense, please let me know. If it didn't, please let me know. That way I can explain it a little bit better. Anyway, any other questions or requests or spice can be sent to uh, my AOL account. I'll have it on the video, or you can post any questions on my YouTube channel. Thank you for watching.